of topics with advanced send-up. We'll talk about the relative versus actual numbering and equivalencing, and then we'll talk about how to extend the capabilities of Cinda by developing Fortran code. So Cinda's data structures, when you list the submodels, you're going to have your header node data in my submodel, and you have header node data in my submodel. This should be my submodel 2, rather. And so I have a diffusion node, an arithmetic node, a boundary node, a header node. This is the order that it's always going to store the data in. So it's always going to do all the diffusion nodes first, and then subsequently it'll be all the arithmetic nodes, then all of the boundary nodes and all the header nodes, regardless of the order you put them in here. So here I put in a boundary node, an arithmetic node, and a diffusion node. But the way it's going to be stored is that all the submodel ones are kept together. So this is really going to be 101, this is 102, 103, 104. But here, in this case, this 101, which was the third one that was entered, is the first one in this block for the submodel 2. And then it will be the arithmetic node, and then the boundary node next. So knowing that that's how it stores it is a bit of an important characteristic. You'll find that if you use some of the routines, there's an nstart, a nmdif, number of diffusion nodes, and the nmari, number of arithmetic nodes, number of boundary nodes, number of header nodes. The nstart for a particular submodel would be this location. Then how many how many diffusion nodes, how many arithmetic nodes, how many heater nodes, how many boundary nodes, how many heater nodes. So knowing that it's always going to store it in a consistent format would let you take advantage of things. So if I wanted to set all of the arithmetic nodes to 20 degrees C for a particular submodel, I could see, all right, let me find where that submodel starts, go the number of diffusion nodes, and then start there for the number of arithmetic nodes to perform some operation on it. So just keep in mind this is how it's grouped. Similarly for the conductors, they're grouped in the input order for submodels, and then all the linear ones, and then all the radiative ones. So even if you did, linear, linear, radiative, 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 linear, linear, radiative, radiative, it's all going to be linear, 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 radiative, 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 radiative. So regardless of the order that you input them, this is how it gets stored in there. And so this is the relative number. So when the preprocessor goes through and you tell it submodel 2.t101, you're really going to see is T parenthesis 5. So what happens is all the temperatures are stored in one giant T array. And each index in that array represents a particular node. Similarly for the conductances, similarly the capacitances would be the same, Qs would be the same. So that's the data structure that it has for the node data and the conductor data. When you need to go back and forth between these for some reason, there's an nth node or an node trn. This one is a function, this one's a subroutine, where you can say, let me give you the actual number and you tell me what the relative number is. Or let me give you the relative number and you tell me what the actual number is. So there's also an array trns if you need to do arrays to convert that. But understanding this, understanding how to do it, does allow you to do some things that would be difficult to do manually if you're trying to do it. The array data structures are even a bit more complicated, and there's something called equivalencing. I have not seen this in other programming languages, but Fortran does it, where I can equivalence that two variables or two arrays occupy the same space in memory. And so if I go and say, give me the integer value of index number 3, I'll get whatever the integer representation is of the bits that are in there, even if I stored it as a floating point. So that can really get you into trouble if you're not very careful with what your data types are when you store it. So the way that an array is stored is it is a mix of both floating point and integer values. The integer values are the number of entries in that array number. So here we've got array number 1, it's got 1, 2, 3, and 4 in it. Array number 10 has 2.3, 3.2, 3.3. And so array number 1 starts here, has 4 entries in it. So then it knows when you pass in array 1, okay, I go 4 entries, this is the data that I need to work with. Array 10 was 3 entries, so it's a 3 in the integer variable for this, and then it knows to go 3 entries there. A11, well, I've got 1, 2, and 3, it's storing that as integer values, and array 21, if I were allowing mix array, could straddle and have some of these in here. So I could go and say, give me array index number 16 for an integer, and it would give me gobbledygook. It'd be gibberish because it's whatever the integer representation is of the bits that make up a floating point of 1.0. So this is a way that was used way back when because they had to be careful with memory. I mean, memory wasn't plentiful back in the 60s. So they had to do all the tricks they could to minimize the amount of memory usage. So you didn't want to have a big giant array of integers and a big giant array of floating points that were empty. So this was one of the tricks that they do to do that. So just helps to understand this and this equivalence A array and NA array. So if you ask for an NA, it will give you the integer representation of whatever bits are at the address that you have requested. If you ask for a floating point, then you'll get the floating point representation there. All right, so most of Cinda's data, all those T's and Q's and C's and G's is accessible through Fortran. The only real exception is you can't figure out exactly what's happening internal to any of their library routines. So once you go into a library routine, like let's say you're calling the heat pipe routine, you can't do anything or change anything with what's inside there. It's a black box. It's got ins and outs, and that's all you can do. But outside of that, you can have these things. So if you need a subroutine, you can insert it into the user subroutine data. If you want access to all of the Cinda variables, you do an M-type call common. And what that's going to do is it's going to make all of those variables accessible to you. All the T's, all the Q's, all the G's, capacitances, and everything will all be there if you need to do it. So it gives you that plus all the control constants and other Cinda data structures. So if you're in a subroutine, you're writing your own subroutine, put in a call common to be able to access all of the other Cinda things globally that's in there. There are a variety of variables at your disposal. N node is the total number of nodes. M mods is the total number of submodels. There are arrays for ND name. This is the same size as the number of nodes. This contains the submodel name for each node. There is an NDINT. This is the node number portion, also the same size as the number of nodes. So I can get the submodel name and the integer portion if I wanted to loop through 1 to n node. Size for M mods, this is N mod. This is the list of the submodel names. Clearly it's going to be sized for the number of submodels. And then what I talked about a little earlier, this is N start, number of diffusion nodes, number of arithmetic nodes, number of boundary nodes, number of heater nodes. So this helps you to figure out where a particular index is for a particular submodel. If you know the start, know how many diffusion nodes, how many arithmetic nodes there are, you could then go and do something with all the boundary nodes. So these are some things that are available to you. You also have all of the relaxation criteria, both the requirement and the calculated values for arithmetic, diffusion. You've got the capacitance divided by the sum of conductors. Each of these is specific to each submodel as well. So you have that for the size of M mods. And this should be M, not N. So those are some variables if you really want to get deep into the weeds. So let's talk a little bit about the thermal calculations and what's happening. So you call steady state, and what's going to happen? Well, it enters. It goes through variable 0 for submodels 1 through n. It then goes through variables 1, submodels 1 through n. Solves for the temperatures. Checks to see if the relaxation criteria is met for each of the submodels, both arithmetic and diffusion. If it is met, then it checks to see if the energy balance for the system is met, or sorry, energy balance for the nodes is met if you're checking this. If that's met, then it checks to see if the energy balance for the system is met. If all three of those are met, then you exit out, you've converged, you go to variables 2. If any of these are not met, you didn't meet the diffusion nodes, you didn't meet the energy balance at a nodal level, you didn't meet the system energy balance level, you check to see, have I hit the maximum number of loops? If I have, well, I'm going to exit out. I'll tell you that I exited out and here's the maximum number of loops. If I haven't, I increment the loop count by 1 and go back through all this and do it again. So it is an iterative process. There is the nonlinear aspect of radiation. And eventually, you're either going to converge or you're going to hit the maximum number of loops, at which point you'll return to variables 2, do whatever instructions you've asked it to do for submodels 1 through n for variables 2, and then go to output calls and then exit and return back to operations block. So this is kind of the programmatic flow chart for a steady state solution. Transient gets a little bit more complicated. We're going to, again, come in through the entry here. We're going to go through variable 0. We're going to check to see if we go through variables 1. There's a flag called nvarb1. If this is 1, then it's saying go through variables 1 each iteration. If it's not, then it goes through 1 time. So we'll do all the instructions in variables 1, and we'll solve for the temperatures. We'll again check to see, did we meet the relaxation criteria? We may also check to see, did we meet the forward-back energy balance? If not, we increment the loop count and go back here. If we did, we're going to check to see if we've hit the maximum number of loops. If we have not hit the maximum number of loops, we're going to check to see, do we meet the maximum temperature allowance per time step. So this is the maximum temperature allowance per iteration. This is the maximum temperature allowance since the last time step. So this basically prevents you from taking a 30-degree jump over 1 second if you want to make sure you do that. So if you do exceed this, then they reset the d time u, the time that's used, to a smaller value, reset all the temperatures to their old values, reset the loop count back to 0, and try to solve with a smaller time step. So if you're basically said, hey, I only wanted you to go no more than 5 degrees over a time step, and I went 30, it'll back up and try a time step that's probably 1/6 the size as a first order. So if you look in the solution and you see time step reduced because node such and such DTM-PCA exceeded requirement, that's an indication that you fell into this part here and exceeded your maximum temperature change per time step that you allowed. You did hit the maximum number of loops, or you were okay for your criteria here for the didn't jump too far, then you go through variables 2. Do you need to go to output? If you do go to output, you go to the output calls. If not, then you check to see is the current time equal to the end time. If not, then I increment the time. So I set time O back to the current time N. I set time N added to the new time step to move forward, and then come back through here again. So you basically keep going through, increment the number of loops until you've converged. Once you've converged, you move on to the next time step, and you keep doing that until you have hit the end time, at which point you exit out with some stops along the way to output calls. It's a little bit more complicated, but still fairly straightforward. So what it's doing when it solves for temperatures, there are 2 methods that it has for solving. There's a matrix solution and a iterative solution. The matrix solution to me is a black box. It's magic. Somehow they do the advanced multigrade conjugate gradient stuff that academic types would probably understand better than me, but they take the G matrix, they invert it, they multiply it by the Q vector, and they get the temperatures out. They do have to take all of the radiative terms and linearize them. So if you take a Ti to the 4th minus a Tj to the 4th, you can separate that into Ti plus Tj times Ti squared plus Tj squared times Ti minus Tj. And so there, when I take those 2 terms that are here, I can linearize that and get all of my radiative terms into a linear solution that can then be solved. As such, it does take some time to do that linearization each time. It's not a free computation, but it is probably fairly small in the grand scheme of things. There are 2 matrix solutions that they have. There's the YMSP or YSMP, the Yale sparse matrix package, and what they use now is generally is the advanced multigrade conjugate gradient. This one, if you set MAT equal to 1 or 2, uses the Yale package. The 11 or 12 uses the conjugate gradient. The difference between 1 and 2, 1 says, let me solve each submodel by itself using this approach, whereas 2 says, let me solve all the nodes together that are using this in that approach. Similar for 11 and 12, it's the same way. I don't know, in case you aren't familiar, ANSYS has recently bought CNR. They've acquired them. They're in the process of coming over. I don't know what the plans are for whether there would be some improved solvers coming in the future, if ANSYS could leverage some of that capability. That's an area I would certainly like to see, is anything that we can do to speed up the temperature solution, particularly if there's any way to parallelize it. So I'm hoping that in the future there will be some further versions of MatMet that would give us faster solution times. But that's for CNR and ANSYS to work out. The iterative method is the old way that things were done before you had some of these matrix solutions. Uses a lot less memory and such. And basically what it does is it says, okay, I'm going to solve this node temperature, holding all the nodes around it as constant. And then once I have that node's temperature, I'm not going to move to the next node, and I'm going to solve all those nodes, solve that temperature based on the updated data that I have and everything around it. So it's very much a ripple kind of effect. You know, I throw a pebble into the pond, and I've got to wait for all those ripples to work their way out to the edges of the pond in order to get that. It does work fairly well. It'd be interesting to see if they parallelize that, if it could be done faster. Be curious to see. But it's one of the reasons that you wish to avoid very, very, very large conductances, because what it does is it makes things very numerically stiff. And so one time I solve for temperature of I, and it's yanked hard by what J is because it's coupled to it. And the next time I come through and I solve for J first, and it's yanked back the other direction for I. So you basically get this oscillatory behavior that just doesn't want to converge well. The matrix solutions tend to avoid that, but it's still a good idea not to use really, really, really high conductances to try to make two things go to the same temperature. There was some things in the iterative solution to solve from 1 to n, and then solve from n to 1, and then solve from 1 to n going every other one and backfill the other way. And so you tried to introduce a little bit of pseudo-randomness to it, so it wasn't always trying to do it in the same order. And that's what can cause that oscillatory behavior for iterative solutions with a stiff matrix. Selecting a time step. CNR and I will agree to disagree on this. They suggest everybody uses D time I, which is an automatic time step solution. I'm not exactly sure how they select it. I think they start off with some training data and see where it goes. There is a term called CSG min, which is the capacitance divided by the sum of conductors, C divided by SG, sum of Gs. If you look at the units for that, it's watts per K divided by joules per K gives you second. So that's a measure of what's the biggest time step I can take before I might have some problems. For that reason, you wish to avoid very small capacitances. If it's very small, it drives the CSG to a small number. If the capacitance is very small, why isn't it arithmetic? Assume that it's a massless node if it's so small that it's driving you to small time steps. Similarly, a large conductance makes for a small CSG. And if you have a very large conductance, let's say I made a conductance of 500 watts per K between two nodes, well, they're going to pretty much run at the same temperature. You know, I need to have 500 watts to get a 1 K difference between them. Well, if that's the case, why didn't I make them the same node? Why do I have two nodes there with a very, very high conductance? So these are things you wish to avoid in order to keep the CSG from being too small and driving your time steps small. Also be careful of using a very small thickness in thermal desktop, because it's not necessarily going to recognize that you put in a 1 mil thickness for an adhesive, and it will make a huge conductance because Ka over L is 0.0001, big number. You know, we've had that where some vendors had put in a model and they modeled the adhesive in there, and so the heater's down to the substrate. It's huge conductance and made things not behave very well. So avoid that kind of stuff if you can. If you are using the D time I equal to 0, There's some useful information in the output file. If you search for the string that says this submodel contains time step limiting node, it will occur at various places throughout there. I think every time step might be that it's in this submodel one time and this other submodel another time and a third submodel another time, but it can help point you to, hey, this one is doing something that's driving your time step small. You might look at what the network is doing around there. What are the conductors? What's the capacitance? See if you can understand why it's doing what it's doing. D time L and D time H can be used to prevent the time steps from going too small or too large. If the calculated time step is greater than D time high, then it sets it to that. If it's less than D time low, it usually terminates with an error message. More often than not, from my experiences, if I haven't very carefully conditioned the model, it's going to take much, much smaller time steps than I really want it to. That's why I tend to say, let me just, as an experienced engineer, decide that, you know what, things don't happen faster than probably 30 seconds in thermal. Not to the point where we really care about it. Yes, MLI might skyrocket in 30 degrees, but I don't care about MLI. Most of the things we have tend to be slow-moving things. So software vendors cautions against setting D time I equal to your own value. I tend to say it's probably okay. I did do an example just to see what happened for one of the sample models. If I ran it with the automatic time step selection and with a D time I of 30 seconds, you can see that it ran about 10 times slower. Okay, maybe I don't care for 50 seconds versus 550 seconds, but if it takes an hour to run, then 10 hours is a bigger deal. By and large, all the orbit average nodal temperatures were within 1 degree. There were some places where MLI nodes had some considerable differences. Kind of scratched my head as to exactly why that was, but I think what I traced it back to is that when the solution is doing the interpolation between 2 points for a time step, it's going to use an average of the current time and the previous time step. So if I had some kind of a sharp change here like this, like coming into or out of eclipse, and I did 30-second time steps going from here to here, well, it's going to give me this value. But if I were 2-second time steps, it's going to give me a higher value. So yes, you may find some things where it behaves a little bit differently, but usually they're low mass things that are going to respond very quickly, or which tend to be things we don't care about. Might be worth running it one time, but if you got to run it over and over again, kind of come to the conclusion that 30 seconds, a minute, 15 seconds, 10 seconds, probably good enough if it runs 10 times faster than it would if I just let it choose it on its own. So, all right, other questions that I often get: how to troubleshoot a slow running model. There are basically 3 areas to address for a slow running model. It's taking too long for each iteration. It's taking too many iterations to reach convergence, or it's taking too small a time step to finish the transient. So too long per iteration, there's really not much you can do about it. Usually it's caused by too many conductors. The more conductors you have, the bigger the matrix, the more dense the matrix, the longer it takes to invert it. All you can really do at that point is try to reduce the conductors and throw away the smaller terms and hope that the accuracy impact is negligible enough. Sparse G might help. It tries to ignore the smaller terms. So what it does is, as I said earlier, takes the sum of conductors times the sparse G value. If a conductor is less than that, it temporarily sets that conductance to 0. So it attempts to sparsify the matrix. Too many iterations. Usually your convergence criteria may be too tight, or you've got perturbations. So if it keeps taking a lot of iterations, might be that it's just not making progress to not change by more than a millikelvin or a tenth of a millikelvin. Maybe relax that to 10 millikelvin instead of 1 millikelvin. Or you've got a heater that is continuously cycling. Some of the proportional heaters, if you try to use a proportional in steady state, if you have too tight a band, well, you take the gain for a proportional heater is divided by the available power divided by the bandwidth, or the dead band. Well, if that dead band is small, it makes for a very large gain. If I have a large proportional gain, I can get oscillatory behavior. So sometimes widening the range of temperatures for transient or for a proportional heater can make it behave better in there. So usually what's happening there is something is keeping it from converging. At that point, what you would want to do is every 50 loops, 100 loops, whatever you're comfortable with, output all of the things that haven't converged yet. And this is a place where developing some code to do that, and I have it if anybody needs it. To output, here are all the submodels that haven't converged. Here's a node number that isn't converging yet. Here's the value that it is. And you can start to see, hey, is it always the same node? Is it always the same submodels that are causing problems? I think there's a convergence trace example in this in a little bit, but having that information at hand is very, very useful. So you can get that out of Cinda. There's the ND RLXCC. So these give you the node and submodel ID for the relaxation node. For diffusion, this is for arithmetic. And then there's this convergence trace code in the advanced Cinda model, which basically I'll output probably every, I think it's 50 iterations in my steady state numbers, and then transient, just to say, hey, which submodels are that are causing me to not be converged. And then lastly, if it's too small a time step, for me that's usually caused by the automatic time step solution, which could be driven by very small capacitance, very large conductances. A secondary one is that you could have a DTM-PCA or ATM-PCA that's responding to a very large flux change over a small time. So, if you suddenly go over a 1 second and you change to, 100 watts of power, it's going to be hard to not, on MLI, it's going to be hard to find a number that's small enough to not go more than a degree or 2 degrees or 5 degrees over that time. So usually that's the secondary cause if it's not driven by the CSG type behavior. Okay, perfect. All right, so any questions on the advanced Cinda? I know that's a little dry and a little deep material, but I'm happy to address any questions or inquiries anyone has. Usually not, but most of the time we're solving the entire matrix as one. So there may be some speed performance optimization you could do if you tried to solve each submodel by itself. If they're very weakly coupled to each other, maybe there's some things that could be done, but it's so specific to a model. You'd have to spend a lot of time playing and trying and trial and error to see if there's something. But I think it'd be trying to squeeze blood from a stone. There's just not much to get out of it. So you take a 5-hour run and make it run in 4 hours and 45 minutes, and you took a month to make it be that much faster. It's just diminishing returns, as they say. Usually for me, if it's running slowly, I want to dive in and figure out what is it that's making it run slow. Who's not converging? We've got everybody in this room. Somebody's not converging. Which one of you is it that's not converging? And let me go address why you're not converging. That to me is the best place to go. And do I have the convergence trace in here? No, let's. All right. Of what I got out from when I ran the convergence trace. So this is the time step. This is the number of loops. And so here I've written it such that it's only going to tell me the ones that haven't converged yet. And so I can see, well, these are the areas that I probably need to go focus on. These are the submodels and what they have achieved and why. I think this is a little old. Nowadays, I think I put a percent sign beside it so that it pops out as to what hasn't converged. But knowing which submodels haven't converged and what their values are lets me address specifically where in the model, when I've got 200 submodels, it's usually 10 of the 200 that are causing me to slow down or not converge. So that lets me address it. If I see the same submodel coming up and I see the same node in the same submodel coming up, definitely know where to go. Or I see the same few nodes coming up. It helps me to address where something is ill-formed in the solution to converge in the time frame that I would like. So, but it does require that you have to ask the model more frequently, hey, how you doing? I'll ask each of you, have you converged, have you converged, have you converged? And okay, well, if there are 5 of you that say you haven't converged, now I know which 5 to go look at. Does that answer the question? Does that help? Are you saying whether you made something arithmetic or diffusion?
Sorry.
So when you say classify the node, I don't
Node
understand what
to
you mean.
the
So whether you put a node in submodel A or submodel B, it really doesn't change its behavior.
okay.
The only way that it would is if I had that node and I said, okay, for submodel A, I want you to give up or call yourself converged when you've only changed by 10 millikelvin. But for submodel B, I only want you to call yourself converged when you've changed by 1 millikelvin. Well, the submodel A at 10 millikelvin will converge quicker because I can allow a greater tolerance for error than the 1 millikelvin case. So that would be the only time where it makes a difference, is if you have different convergence criteria for that particular submodel as far as the node goes.
Okay.
Clear? Back in the back. I don't. I tried to use it on a very small model. It was just an optic in a test, and I had 10 thermocouples, 10 sensors locations, and probably 10 different uncertainties. I tried to do it with some Excel and sensitivities, and it seems so great on paper. It just doesn't translate well to work in practice. If you have 1 or 2 variables that are really driving the solution, I think it could work well. By the time you get to many variables and they all have very small effects, I just don't think that it performs as well as it would seem to when you first hear about it. When I run the Roman Space Telescope, I think it's somewhere between 150 to 200,000 nodes. To me, it's not as much the node size that's the driver as much as the number of conductors. So the number of conductors makes the model run slower. So I could have 10,000 nodes in a model, but if I have 30 million conductors, it's going to take about the same amount of time to solve as if I had 100,000 nodes and 30 million conductors. So it's really the time to run the model is driven more by the number of conductors to me than just the node count. So. So the wavelength dependence is not really handled in there. They have a checkbox for it, but I don't know that anybody has really used it. It basically is banding the wavelengths into two spectra, to the left of about 3 microns and to the right of about 3 microns. Generally speaking, it's probably good enough for most things, but if you do have a more complicated cryo type application, you might have to be more careful. I believe that probably a decade ago, Como and Ring did put out a white paper on how to deal with non-gray radiation, where you come up with different levels of emissivity that translates to absorptivity as a function of wavelength bands, and then you have to conglomerate those conductors back together again for it. So it's not something that I think is done often enough that they have spent the time to really address it. And if Webb didn't need it, it's hard to see who else would on a frequent enough basis, but if it's something you need to be concerned with, it would probably be incumbent on you to understand how to set your properties appropriately for multiple bands of wavelengths. So you could set up different RadCat optics files that represented different wavelength ranges in order to be able to do it, and get different sets of RadKs for those different sets of bands and include all of those in the solution. Does that make sense? There was a question over here to the left as well, I thought. So you can see the number of iterations if it, so yes, in the output file, it'll tell you how many iterations it had. You could also write logic in variables 1, or any time you could say, what's the loop count? Loop count is a variable, LOOPCT. So if you want to know that, that will tell you what the current loop count is. You know, the trick is whether it's needing a lot of loops every time step. So one of the things I have is, you know, each time step, tell me how many loops you needed to reach convergence. And I like to look at that and see, is it always about 5 to 10? Are there some times where it jumps up to 50? Does it stay constant? But loop count is a variable that you can output at any time to an output file or a user file or anything like that.
Right.
Yes, if you don't wish to look through the output file. The output file does tell you the number of loops when you go there, but you're only doing that every output iterations. So I might solve every 30 seconds, but output every 300. I don't know how many loops it's taking at each of those 30 seconds. I only know how many loops it took for the time that I output at 300 seconds.
Okay.
So if you wish to know more frequently than the output interval, then you need to write your own logic. If you want to look at just the output interval times, you could get the information there. You're welcome. Well, so it's different. For the time step, doesn't really affect the heaters so much. The heaters will affect convergence. So convergence is how much I'll allow a change since the last time I tried to solve. Time steps are how far do I advance in time in a transient solution in order to get to the end. So if you wish to get heaters to behave better, one of the things that I have played with is after a certain number of loops, start tallying up how much heat a heater has been applying. So let's say I let it go for 50 loops, and then for the next 50 loops, I'm going to sum up the heater power. And then I'm going to divide that sum by 50 loops and apply it as a constant value. So now my heater that had been oscillating like this, I'm going to now average and let it stay at a flat line. And now without this oscillatory behavior, that flat line gets to convergence better. One of the challenges we've had on the Roman Space Telescope, is we have 150, 200 PID controllers. And there's just no good steady state emulation for that. So what I developed, and there's a paper in ISIS, if you're interested, I can send you the link, was basically something that did something very similar to that. It said, let me get an average temperature or an average power, and then once I've held at that average power for 10 iterations, let me see whether I'm at the temperature range I want to be. If I'm a little bit too cold, increase it slightly. If I'm a little bit too hot, decrease it slightly. And when I cross over the time step, then I know that, okay, I've gone too far. Now let me decrease the amount that I do it. So first I jump like this, then I jump like that. That's too much. Then I go half, then I go half, and each time I cross, I reduce the amount that it allows it to deviate from there. So that lets it get to a better convergence spot for PID heaters. But basically, the trick is you need to do something to prevent the heater from wanting to oscillate. Sometimes that can be widening the range such that you dampen the gain. Other times it can be finding ways to say, let me smooth out over time or over iterations the oscillatory behavior to a constant value. So you're asking, is there a better value to use than the default? I honestly have had a hard time really understanding how the damping works. It's not very intuitive to me. What I would try is just trial and error. If I double it or if I have it, do I get any better performance? So I would think that if you make the damping factors smaller, it would allow it to go less, but it might be that you need to increase the damping factor to dampen it more. I'm not exactly sure which way it goes, so I would just have to try it and see what happens. But yes, that damping factor is not something that is obviously intuitive of what the value to set is. So,
Okay.
sorry I don't have a good answer for you, but I would try it both ways, higher and lower, and see whether you see a performance in that or not. And something to do, if you do that, is write your own logic such that at every iteration, you output the power and the temperature for the heater. So then you can really see, okay, what is it doing, as it marches through iterations? Is it oscillating more? Is it oscillating less? So that you could get the data to be able to evaluate better, rather than just say, okay, well, tell me what the final number is. Get intermediate data to understand what the trending is as the solution is progressing. You're welcome. For which parameter do you mean specifically? All? No. I usually take 001 for the ARLXCA and DRLXCA. So when it hasn't changed by more than a millikelvin, I think that's pretty good. What I'll often do is see is there's something that is changing because there's a heater cycling. And every time a heater cycles, well, now I'm far away from where my solution was. Do I really care if I'm accurate to a millikelvin on something that's changing 7 or 8 degrees? So where I see that there's a heater, on a panel deck or something like that, okay, I might relax that convergence criteria to 0.01 as opposed to 0.001. But usually I take 0.001 as a starting point, see what areas may be relaxed based on things that are taking longer to converge. For the DTM-PCA, usually let those stay with whatever the defaults are, but there may be times where I want to say that the stability needs to be better. So if I have something that can't change by more than a degree over 30 seconds, then I would certainly set the DTM-PCA to something less than a degree so that I don't go too far. The Fabebula, the EBAL, NA, I usually leave as 0 so that they're not doing anything. I have not found those to help with the solution converging as much as the relaxation criteria, the RLXCAs. Make sense? Good? You could optimize it to some degree by your DTM-PCA. So if you know you have a big flux that makes a big change in temperature, you could say, I don't want you to change by more than 4 degrees or 3 degrees. And when you get to that big flux and it goes and it's got you suddenly went up 30 degrees, it will back up and try the smaller time step. So you can have it do it. It's a little bit of a cost penalty because you're trying things and it's not working, but 1 or 2 iterations or 1 or 2 time steps that you lose out of the whole thing to not have to take tiny time steps the whole time is probably worthwhile. So if you have something that's going to cause a very large change over a very small time frame, I would probably use the DTM-PCA to catch it, stop it, back up, try a smaller time step in this area, and then proceed back to the bigger time step once that event has passed. Well, are you talking the automatic time step calculation?
Yes.
Yeah, I don't fully understand how their automatic time step calculation works. I think it's looking at 4 different points and trying to extrapolate from that what the optimum time step needs to be. I've just found that by and large, unless I've been really careful with the model and don't have the things that drive the CSG to a small number, I just end up having to wait forever for it to solve, rather than saying, hey, you know what? I'm smarter than you are, use 30 seconds, don't use what numerically is an optimum value. So what you could also do is you could change the time step as you march through the solution. So you could say, all right, you know what? I want you to take 30-second time steps, but once you're within 30 seconds of this thing, I want you to change the D time I to be 1/10 of a second, and then start going very, very slowly. Okay, now we're past this. Now reset back to that.
Oh,
so
so-
the D time I is a variable
Oh.
that you can adjust as the solution is proceeding. So it's another variable. I think it's actually per submodel, but that doesn't make any sense to me because it doesn't solve one submodel at a different time step cadence than a different submodel. So why it's not a single global variable, I don't understand, but I think that it is submodel specific. So if you needed to set it, you'd have to loop through all the submodels and set the D time I for that submodel to the new value. But I
Okay.
believe that would be a better way to do it if you know in advance when your event is happening and you want to slow it down for that so that you don't miss it